Hello. And let's see. All right, so let's start with questions, and then I want to talk about Lab 6, and then we'll continue talking about Verilog. But let's start with any questions you might have on homeworks, labs, things like that. How's the homework coming?
Truthfully, I'm starting it today.
Okay. All right. Well, I plan to go through and make a few comments on some of the questions, especially the one with the event detector and the traffic light system. So we'll go through some specifics there. Oh no. Well, you've got a homework question on it. To implement it in Verilog, but it's a whole lot easier in Verilog than it is on a protoboard. And then in 270 we do it again, but we implement it in code, and that's even easier than implementing it in Verilog. So it gets better and better.
Is there any sort of like wait functions in Verilog, like JavaScript-based
So we don't have a wait function per se, but we do have a notion of a clock. And a lot of times in our Verilog circuits we have clocks coming in. We'll do this today with state machines. But for the homework question where we talk about the traffic light, I say assume you have a 2-second clock available, and so we can use that to implement our yellow light delays. All right. Well, let's wrap up Lab 6. You know, that was clearly the most complex circuit of the course to try to build on a protoboard. So I think I saw 6 protoboards as the most that someone used. And you probably need at least 2 or 3 minimum to set this circuit up. So a few comments on here. First of all, let me go over once more what you need to have for a schematic, right? So a schematic is not the same as a picture of your Tinkercad circuit. And a lot of people didn't have a schematic for experiment 1, they just had a circuit. If you have a picture of a Tinkercad protoboard, how is somebody else going to reproduce what you did? How do they know what all those parts are, and so on and so forth? Put a schematic in, right? And with a schematic, if you have an AND gate, draw an AND gate. If it's a 2-input AND gate, draw 2 inputs. If you have an OR gate, draw an OR gate. If it's a 3-input OR gate, draw 3 inputs. If you have something like a D flip-flop, you're allowed to use a box for that. Label it, like D flip-flop. Specify the D input, the clock, specify the Q output. So you make your logic diagram using logic symbols for standard blocks like AND, OR, NOT, and so on and so forth. If I want my output to be inverted, right, make an inverter. If I want to take the complement of Q and connect that to this input, don't just draw a little circle here, because we don't have a physical device that's a 2-input AND gate with 1 input inverted, right? Make an inverter. So this is the beginning of your schematic, right? It's the logic diagram where you're using symbols for logic gates, you know, boxes for things like flip-flops or a 555, standard symbols like this for an LED or a resistor, and so on and so forth. And then to make this a full wiring diagram, right, you need to indicate part numbers. So this is going to be one chip, this will be another chip, this will be another chip. If I have this going into an AND gate, is that going to be yet another chip, or is this going to be the same chip as that? That's up to you as the person making the schematic. But, you know, if you're going to implement this, you probably want fewer chips rather than more, so unless you're, you know, breaking it into 3 logical pieces, like you might have done with a traffic light, you know, you might put these in the same physical chip, or you might have different chips. But you got to indicate that on the schematic. So we label these, right? I would label this U1, and I might label this U1. And then we have this component ID block. And there's a name. There's what type of device it is. There's where we supply power. There's where we connect ground, and there's which pins have no connection. So U1 is a 74.
Would you ever use like a column for clock?
Not in the component ID block. Component ID block is really just showing when you have the symbol, what kind of chip is it, where's the power and ground connection, and which pins don't get connected to anything. And for example, here's our set pin, and our set pin needs to go through a resistor to 5 volts, right? And I don't forget which pin this is, it's either 1 or 4. Don't put that up here, that's not a power connection. That's an input that you want to set to logic 1, but that goes in your schematic diagram, right? This is just detail here. This is really saying, you know, here's a chip, that's what type of chip it is. This is where I'm going to connect power. This is where I'm going to connect ground. This is how you hook this chip up, kind of independent of what you're doing with the chip, right? And then no connection, just list which pins don't have anything connected to them. So here's U2, and that's a 7432, I think. And maybe this will be U3, and that's a 7474. And so on. And then you put in your pin numbers. So maybe this is U4, so I'll go in on 1, out on 2. Here I'll go in 1, 2, out 3. I'll go in 4, 5. I'll come out 6. D is, I don't know, pin 4 and 6 and 7. I don't know what the pin numbers are on the flip-flop, right? But when you're done, you have a picture that tells you exactly how to build your proto board, right? And now you just get a proto board, you grab one of each chip that you have in your component ID block. If you've got 2 separate AND gates, you'll have 2 entries up here for an AND gate. So you grab 2 AND gates, right? And you put these into your proto board and you just start making wired connections. Well, wire from pin 2 of this chip to pin 1 of that chip, plunk in your wire, that part of your circuit's done. And then, you know, the reason that I keep saying do the schematic first is that then once you've got your circuit, if your circuit doesn't work right, you can debug it instead of you know, staring at it and hoping you see where you put a wire in the wrong place. You can actually run your circuit, look at voltages at different points, and figure out with your schematic where exactly the problem is. So those are the elements we want in a schematic diagram. All right, switches. So at one point a few weeks ago, I made the observation that everybody in class seemed to be wiring their switches perfectly, which is very rare. About a quarter of the class has gone back to miswiring their switches. So here's how we wire a switch. If we have, you know, some block over here and we want to send in either a 1 or a 0, here's the way to do this. Take your input, tie it up through a 1K ohm resistor to 5 volts, and then take a switch connect the other end of the switch to ground. Alright, and the effect is if I close this switch, this point is at logic 0. If I open the switch, this point is at logic 1. This is logic 1 because it's pulled up through a 1K resistor to 5 volts. This is logic 0 because even though this point is pulled up through a 1K resistor and this is 5 volts here, this direct connection to ground makes this logic 0, 0 volts. Alright, so I can open it up, put in a 1, I can close it, put in a 0. And what you don't want to do are any of the following. For example, right, this is not a good way to go. So what's the problem with this circuit?
No resistor.
No resistor.
What's wrong with not having the resistor?
I don't know if it works. I've never wired it.
It's free to flow through VCC even if it's closed.
It's definitely going to go to VCC, right? If I close it, what am I doing? I'm creating a short. I have a direct wire from 5 volts to ground. If you do that with a power supply, a little red light comes on and it clicks and it says overcurrent. But if it didn't have that protection, something would start to smoke eventually. This is shorting power and ground together. So that's never going to work for us. Another approach that some people are doing is this. And if I close the switch, that will not create a short, right? Because the connection from power to ground will have to go through this resistor, which is usually like a kilo ohm. So it's not going to create a short and you know, draw too much current. But is this ever going to change the voltage level at this point? No. This is always going to be at 5 volts. It's connected directly to 5 volts right there. So that's not going to work for us either. This is another way that people are wiring switches. And this will probably work in Tinkercad, and it may work in some circuits. The effect here is if the switch is open, this input goes through a resistor to ground. If I close the switch, this input goes directly to 5 volts. So open is a logic 0, closed is a logic 1. And for Tinkercad, that will probably work. But there are a lot of circuits that if I feed this to the input of the circuit, the chip will fail. In particular, there are some very expensive microprocessors that might cost you $50. And if you take this circuit and hook this up to an input pin, and you close this switch, that input pin will fry. Because closing this switch allows, theoretically, unlimited current to flow from 5 volts into that pin. Now, Tinkercad doesn't care about this, and the inexpensive chips we use in the laboratory mostly don't care about this. But more sensitive components, right, we don't want to allow essentially infinite current to flow into an input. And if you hook up your circuit like this, when we have the switch open, if this is 5 volts, we have a maximum of 5 milliamps flowing down this line. So this not only, you know, allows you to control a logic 1 or a 0, but in the case of a logic 1, it limits the current going into the circuit. All right, the last variation that I'll show is something like this. So let's say we have 2 inputs going into a circuit. right? Something like that. And this doesn't work because your two input lines are shorted together, right? This happens when you're trying to save on resistors, and usually it looks more complex than this, but the effect is you end up shorting your two inputs together. So if both switches are open, you've got a nice logic 1 coming into here. But if I close, say, this switch right here, it not only brings this line down to a logic 0, but also this line. And so you're connecting your switches together even though you have two switches. So go back and look at some of the earlier labs. We had a lab, I think it was lab 2, where we first wired up switches, and I think lab 3 we played around with a bunch of different configurations of switches. And we hooked them up backwards, we hooked them up to LEDs connected to ground or power, and we kind of really plumbed the whole idea of you know, how does this generate a 1 or a 0? And we're going to do this a lot in 270. Right, you're going to build circuits where you have switches driving inputs. So make sure that this makes sense to you, and ask questions if it doesn't. And then along the same lines of this is another topic, which is there are different kinds of switches. And in 250, 270, 120, we always deal with this kind of switch. And this is called a single pole, single throw, which means basically it either connects or it disconnects. Okay, it's the most simple switch we can imagine. And it's really just, you know, two pieces of wire. Do we touch them or do we not touch them? That's all this switch is doing. When you close it, the two pieces of wire are touching. When you open it, the two pieces are not touching. A more complex switch is something like this. And this is called a single pole double throw. And this switch can connect to either here or there. So this is, you know, here's my piece of wire that's, you know, going to my circuit, and I can choose to connect it either to this wire or to that wire. Right? So we can choose one of 2 points that we want to connect this line to, either here or here. And if you have a single pole double throw switch, it's relatively easier to compare to wire up an input like this. For example, I could take this and connect it to ground, and I could take this and connect it through a 1 kilo ohm to 5 volts, and this can go into my circuit. And if I put the switch down here, I've got a 0. If I put it up here, I've got a logic 1. And in Tinkercad, even if you forget that resistor, it still works. And so some people on this lab were working on, typically on the delay circuit, and for some reason weren't wiring up their switch like this, and their circuit wasn't working, and then came across the red switches in Tinkercad. And the red switches are single pole double throw. They're this fancier switch that lets you connect. And then if you connect one end to ground and the other end to 5 volts, that makes it work. But if you couldn't figure out how to get your switch to work and you found a solution by switching to a red switch, make really sure you understand why that worked. Okay, and when I ask you to make circuits on an exam, I'm going to ask you to use, you know, this single pole, single throw switch, the same switches we've been using all quarter. And most people who got the red switch to work, I don't think they realized this is what it looked like, and they were trying to use their old design, and it happened to work because this prevented a short. So again, go back to the earlier labs, go back to how these switches are hooked up, and make sure you understand how this generates a logic 1 or a logic 0.
I used it because it wasn't so huge.
Yeah, is there not a blue one that's that small?
There's not.
Okay.
Yeah.
And you can use this like this, and if you use one of these and you build this circuit, that's perfect, right? Not a problem there. And I saw that done in some cases, but in other cases, right, this was kind of a band-aid on what was originally not quite correct design for this switch. it. All right, symbols for VCC and ground. So I should have nipped this one a long time ago, but let's take care of this now before you go on to 270 and other courses. This is a pretty universal symbol for ground. Okay, that's really the kind of only symbol that you want to use in a schematic that you assume everybody knows what you mean. This is very standard for ground. You can label it ground GND if you want, but even if you don't, anybody who sees this is going to say, okay, that's a ground connection, that's 0 volts. That's the only symbol you can assume. Now, I think one of the labs used this symbol for VCC. That is not standardized. Don't use that for VCC. For one thing, that looks an awful lot like this. It's a triangle. And the fact that it's going up is not enough. If you're going to use something like this, you better label it VCC or you better label it positive 5 volts. If you do that, then someone will overlook the fact that, you know, okay, well, you got a triangle there for some reason. That's fine. But if you just draw a triangle, don't assume that's going to be VCC. The other thing is, you know, sometimes in 120 especially, we draw a battery symbol like this. And that's positive and that's negative. But that is not an acceptable symbol for VCC. And so I'm seeing circuits where people are doing this to mean VCC, or worse, doing this to mean VCC. And that looks a lot like ground, right? So anytime that you have a voltage referenced somewhere, safest thing to do is label it, right? Either VCC or positive 5 volts. And 0 volts, label it either ground, or you could do 0 volts, but ground is pretty standard. But don't rely on the symbols, except, you know, this one is pretty safe. That's always going to mean ground. But if you want to be absolutely certain, label your voltage points, VCC, ground, that kind of thing. All right, and the last thing I want to mention is LEDs. So the direction of the triangle matters, and the triangle basically points in the direction of current flow. So if I wire an LED like this, my triangle should point to the right. It's pointing from, you know, the higher voltage down to the ground point. If I'm doing like in that kind of weird lab where we put our LEDs backwards, right, then the triangle would go in that direction because the high voltage VCC 5 volts is over here, and then when this side is logic 0, the LED lights up. So the triangle always wants to point in that direction. And the reason it's a triangle is because these things only allow current to flow in one direction. They're a particular type of a device called a diode, and the diode is like a one-way valve. So if I were to flip this around, it doesn't light up because it blocks current from flowing. So that's just kind of what they do. So any other questions or comments on any of that? That's just kind of like picky stuff, but it's stuff, like I say, let's just pin it down now before you go on to other courses, just so you don't get shocked by it later. All right, let's take a look at the labs. So lab 7. I'm going to take it straight out of Canvas. I have a copy of it here, but I can't promise 100% that it's the same. So I'm going to take it from Canvas just to be really sure. All right, so we've been playing with the Aldec tool. Hopefully you've got that up and running, and have been using it when we go through things in class and so on. So the preparation is really just, getting that tool installed, running, getting familiar with it, and so on. Then we got 4 experiments to perform. Okay, so first thing is, right, for each experiment, you want to, discuss the experiment. So experiment 1, design and create a waveform for an 8-bit even parity generator. Okay, so what does that mean? We'll talk right now about what even parity is, which it tells you right here. But put that in your lab report. Maybe draw a system diagram of it to show what the inputs and the outputs are, right? And then you're going to write some Verilog code. Okay, so your experiment needs to include the code. And as I mentioned in an announcement yesterday, right? For the code, copy and paste it from the Aldec tool into your lab report. Just put it in there as plain text. Don't try to do a screenshot from the Aldec tool, because inevitably it ends up fuzzy and hard to read, and then I can't tell what your code's trying to do. So
Quick question.
yeah, go ahead.
So for like the copy and paste, does Aldec do that where it actually reads the command copy and paste?
So if you select the text in the editor window and then I think right click, will bring up a menu where you can say copy, and then you should be able to.
I know that the command prompt when I do my C code, it doesn't do the copy and paste. So I was just making sure.
Okay.
They do, it's just a different command in command prompt.
Yeah, so if you're in a putty session or something like that, there's different ways depending on your environment to copy and paste, but there should always be a way to do it. And it's definitely worth trying to figure out. So like usually to paste in a Linux window, it's Control Shift V, or there might be a right click, or it might be your middle mouse button or something like that. But there's generally a way to do it. And once you figure it out, life just gets a lot better.
You can always open it up in a text editor, and then it will auto format it for you. So Visual Studio Code.
Right.
Open up Verilog and then copy and paste it, and it's all formatted nice.
Yeah, good suggestion. So these Verilog files are just plain text files. They have a .v extension, and so you can open it up in a different tool like that and copy and paste from there. All right, you also want to include the results of your simulation, because you're going to test your Verilog code, right? So run it through the Aldec tool in that simulation window. And the simulation, that you can go ahead and do a screen copy, right? So print screen or shift print screen. Or, some of these tools, you can get them to actually save what you're seeing in your simulation window as a JPEG or a PNG. But experiment with it and get a nice timing diagram, right, from your simulation, but make sure it's meaningful, right? If you're trying to capture 50 events and they're all smashed together in a little blob, can somebody look at that and see if your simulation worked or not? So ask yourself these questions, right? Is what I'm putting in my lab report sufficient for somebody else to know what I did and what my results were? Right, so go back and look at it with sort of fresh eyes, and make sure that it's usable to somebody else who doesn't know what you're doing ahead of time. All right, so let's. Yeah, go ahead.
Do we have to design our own experiment in this one? I wasn't seeing.
Yeah, so new experiment and expected results.
Okay.
And then go ahead and do the experiment. And it's Verilog, so, pretty much anything that you can think of is going to work. And these are kind of like homeworky problems instead of build a circuit. So it's usually not too hard to figure out a different problem. The new experiment does not have to be more difficult than the others. So I've had some people say I couldn't think of anything harder than what we already did. It doesn't have to be harder, it just has to be new. But the idea is, think of what you're learning in this sequence of experiments, and then say, well, if we did this other thing, that would be something new to try, right? So don't just, change your even parity generator to an odd parity generator, right? But think of something along the lines of what you're doing in these experiments, but different. Something that would be a little challenging for somebody to do.
We're going to talk about parity in a second. Right?
We're gonna do that in 1 second. Yeah.
Okay.
So yeah, let's go through the experiments and details. So experiment 1, 8-bit even parity checker. So it tells you really all you need to know. The system will accept an 8-bit input and outputs a 1 if there's an even number of 1s. Otherwise, it outputs a 0. All right. So what does this mean? Let's come on. Oh, I gotta minimize. Okay. Let's think about an 8-bit number. All right, there's an 8-bit number. How many 1s do I have? I have 2 1s. Is 2 an even number? Yes. So my circuit should output a 1. If my input was something like this, the number of 1s is 3. Is that even? No. My circuit's going to output a 0. All right. That's the whole behavior of your circuit. So output a 1 if there's an even number of 1s in your input. Otherwise, output a 0.
Is there like a Modelo in this? Similar to C?
Is there a what?
Like the ampersand symbol?
Oh, yeah.
In Verilog?
There should be like a percent symbol. But there's
Oh, yeah, not ampersand.
yeah, like modulo. So I think there's a percent in Verilog. There's something else we can do in Verilog or in computer science for that matter, to know if we have an even or an odd number. So if you look at a number in binary, the value of this bit tells you whether your number is even or odd. If this bit's 0, then you have an even number. If it's 1, you have an odd number. And that's useful to know in general in life. And this works because, this is the 2's place, this is the 4's, this is the 8's, this is the 16's. Whether you add these or not, right, these are all even numbers, but this is the units place. And the only way that adding all of these up gets you to an odd number is if you include this bit right here, which means you had a 1 right here. So if you're adding your bits together, you could look at the least significant bit and see if it's a 0. Or you could do a percent 2 to see if it's evenly divisible by 2.
Wait, are you saying if the last one is a 0, then it's even?
Nope. I'm saying if you have a number, let's say that you added up, your bits, and you found out if you got 3 bits. So what's the number 3 in binary? It's 1, 1. That 1 tells me that this is an odd number. What's the number 2 in binary? It's 1, 0. That 0 tells me that 2 is an even number. So if you don't like the modulo operator, that's just another way to find out if something's even or odd. But that doesn't tell you if the parity is even. That's just nothing to do with parity. If you have a binary number, you can tell if that number is even by seeing if that low bit is a 0. But that's something you'll find use for in a lot of situations.
I looked at some documentation. It has pretty much all the same logical bitwise and math operators as other languages.
Yeah, it's pretty close to C. I think it does not have a plus plus though. There's something it's missing. I don't remember what exactly. But yeah.
The inversion is like a tilde C, right? I don't think I've messed with that.
You can use tilde and exclamation mark. I think both of those work. I usually use exclamation mark, but I think tilde works also. But these are all things you can experiment, right? Once you've got the flow down for how you write Verilog, compile it, simulate it, right? It's pretty quick to make a change, recompile it, rerun your simulation, see the results. And that's something you want experience with, right? You want to do this enough that it becomes very fluid, right? You want to be familiar enough with it so that if it crashes and goes away, it takes you 20 seconds to get back to where you were, because you've got muscle memory for these steps, that's just going to make all of this that much easier. So yeah, definitely experiment and play around with modulo operator or inverses or things like that.
I'm curious, how often are we going to be using the Verilog in next quarter?
Not at all.
Okay.
So this is the only time at Clark that you'll encounter Verilog in a class. You might end up using it, in a service learning project or something of your choice, but this is the only time you'll encounter it at Clark. And chances are, if you're computer science, you won't encounter it at all at a university. If you're electrical engineering, there's a good chance you will encounter it. All right, there's also a hint in here which says XOR is helpful, right? Why is XOR helpful? Well, because XOR is another way to count how many ones you have in a sequence of ones. If I take 1 and 0 and XOR it, I get a 1. If I XOR that with a 0, I get a 1. If I XOR that with a 1, I get a 0. XOR with a 0 is 0, and so on. So if I XOR all 8 of these bits together, I end up with a 0. Whereas here, if I XOR 1 and 0, I get a 1. 1 and 0 is 1, 1 and 1 is 0, 0 and 0 is 0, 0, 0, 1 and 0 is 1. I end up with a 1. And that's significant. That's related to whether you have an even or an odd number. So play around with that if you like. It's another way to do this kind of calculation.
So if you have a whole 8-bit input,
Mm-hmm.
you chose to just XOR that entire expression, it would know what to do, right?
If you do A XOR B XOR C, yeah, it'll build a set of XOR gates and route the inputs accordingly.
Ah, okay.
Yep. And all of this experimentation, by the way, is like, good stuff to put in a lab report, right? Now, the lab assignment doesn't say, try to do this 3 different ways and document each of your attempts and results, right? But if you end up trying to do this more than one way, or if you try to do it one way and it doesn't work and you end up doing it a different way, right? That can all go in a lab report. That's all part of the science that you're doing, the hypothesis and the experiment and the observations and the conclusions, right? That's all totally legitimate to put in there. All right, so experiment 1 is some kind of combinational circuit. You don't need an always block. You don't need anything like that. It's really just, 8 inputs going in and 1 output coming out. And the output basically tells you whether you have an even number of ones or not. And so a bit of a sidebar here. Why do we care about this? Why would you ever care about how many ones you have in a number and whether it's even or odd? Any ideas? Or have you encountered the term parity before?
No, it's the first
In
time.
terms of drives, yes.
In terms of
This is
drives.
the first time I've heard it.
And
Yeah,
memory.
So let's go back a few decades before we had, nice reliable network connections. And a lot of how you connected computers together was by using phone lines. Because people figured out that, we had a phone network, you could send sounds across these, and if we could translate ones and zeros into sounds, say 2 different tones, we could send binary information from one point to another just using a plain old phone line that was already there. And we didn't need to, you know, create this infrastructure that we have today with, you know, high-speed cable and fiber and wireless networks and all that stuff. We could use the phone system that was already in place, which, by the way, the phone system fought. AT&T went to court multiple times to stop people from doing this, and they won. They won the first few times, and then finally, a judge ruled that you can send anything over a phone line that you want as long as you don't interfere with the actual wires. If you're just sending sounds, you can send any sounds you want. And that opened up the world to, you know, fax machines and recording machines and all that kind of stuff. So
Why didn't they want them using the line?
because big business is very short-sighted usually. That's a whole nother topic, but Bell Labs had a monopoly, right? They had this copper network that connected phones together, and that was their business model, and they were making a lot of money, and nobody else could touch their business. And yeah, they could have, you know, sold fax machines and answering machines and all that. That wasn't their business model. And what they realized was that, you know, if people started using their phone lines for other things, then new markets would develop that they wouldn't be in charge of. And so I think they just wanted to clamp down and say you can just, you know, have conversations with your neighbors and that's it. And this is exactly what happened, right? Once the courts ruled and said you can send any information you want, everybody started making other things that would attach to your telephone, answering machines, fax machines, and modems. And modems were how you would have a computer talk to another computer. And you'd use a series of tones, high and low typically, to represent, you know, 0 and 1, and you could send information over. But it was a pretty error-prone process, because it's just sound, and if somebody yells in the background while my computer's trying to send a 1, the other computer that's listening to it might think it heard a 0. And so I might be trying to send this binary number, and, you know, at the point where this bit's being sent, somebody yells or, you know, my cat screams or something, and the computer thinks that I sent a 1 instead. Well, if these are ASCII codes, this is the ASCII code for an A, this is the ASCII code for a C. And if I was typing in somebody's grade for a course, and I typed an A and the other computer thought I typed a C, somebody just got a C in the course instead of an A. So
you could like talking could mess with the internet.
if you were transmitting over a phone line, and this was back when it was all done acoustically, it was done with sound, and yeah, so let me get you a picture so we can be less abstract.
I did not know that it was actually done from sound.
So this is in the old days.
So bad.
So you had what's called an acoustic coupler, and it looked like this. And the deal was you would basically take your phone, you'd dial up a computer, and then you'd take the handset and you'd push it down into these little rubber cylinders, and it made, you know, a pretty good seal so that, you know, minor background noise wouldn't come through. But if there was a really loud noise, right, it might still get picked up by the microphone and get sent, and it could perturb the information that was going through. Or, you know, the worst case.
About a 90K modem. I didn't know we were going back that far.
This is a 300 baud modem. So this was 30 characters per second, which was not the slowest. This was pretty standard speed when I first got into this stuff, and then 1200 was like the fast version. The worst of this was, you know, if you were using your computer and you were sending stuff over the phone and somebody else in the house picks up the other line and starts trying to call someone, right? So all these things would cause potential interference. And so how? Go ahead.
Oh, I was just gonna say you can see that used in word games.
Oh yeah, totally. And yes, you could whistle to these things and actually get them to do things. But not easily start a nuclear war. So how do we deal with this? How do we deal with the fact that, I tried to send this bit pattern and the computer thought that it received this bit pattern? And one way would be, just send everything twice. And so I would send this twice, and one time it would get this, one time it would get that, and it would say, oh, something's wrong. But that's really expensive. So we want to send a little bit extra information to let the system know that it got the correct thing. So we add what's called a parity bit. And so we might say, for example, I'm going to send 9 bits instead of 8. I'm going to add 1 extra bit over here. And I'm going to pick that bit so that the total number of ones is always even. So if I want to send the character A, this already has an even number of ones. I'm going to set my parity bit equal to 0. And if I wanted to send a C, I've got 3 ones right here. I would set the parity bit to a 1, so now I'm sending an even number of ones. And the computer that receives this, when it gets its 8 bits and it gets its parity bit, it's going to expect that it's seeing an even number of ones. And in this case, it's going to look and say, wait a minute, I've only got 3 ones, something's wrong. And it'll send a message saying, hey, can you repeat what you just said? And then I'll go ahead and send this, and hopefully it gets this, and it says, okay, that's a good number. So this was an early version of error detection. And so the circuit that you're building is something that you could use as part of a transmission system to detect these kinds of errors. And we still use this. We don't send things acoustically for the most part anymore. But when something gets stored on magnetic tape, generally there's a parity bit because there could be an error in how the information is stored. When you have memory in your computer, if you spend a little more, you get what's called ECC memory. That's an embellished form of parity checking. And it basically lets you detect if something that's stored in memory has got a value that's not correct.
Is there parity checking with optical lines also?
There could be. Parity is pretty crude, so we don't really find it being used a whole lot in modern systems. But the same idea is used, for example, with ECC. We have basically 3 bits. And it does a more precise, more nuanced job of checking for errors. So one problem with parity is, if I had 2 bits flipped, it's going to look and say, oh, you got an even number of ones, I'm happy, right? So if I have 2 errors, parity checker won't notice that. And even if I have 1 error, it'll notice that something's wrong, but it has no idea which bit is wrong. It just knows that something is wrong somewhere. These more modern systems can actually like reverse the errors so that you don't have to retransmit them. And so you find this used in storage systems, hard drives, things like that. All right, so let's go on. Experiment 2, 8-bit up-down synchronous binary counter. So we made a counter the other day in Verilog, and we saw that was, basically 1 line of code. Was just, take your register and just, add 1 to make it count up, subtract 1 to count down. In fact, I think we might have done an up-down counter. So we might have already done experiment 2 in lecture, but I think we did it with a 4-bit counter. So that's a good one. Experiment 3, 16-bit shift register. So we talked about shift register design on Tuesday, and I mentioned this would help you a lot with your lab. So this is the experiment, one of the experiments where this is useful. So what's the shift register do? It has an input and an output and a clock. And let's see, circuit accepts input on the rising edge of the clock and outputs the input value after 16 full cycles. So system diagram, it looks like this. The behavior is whatever value you put in, after 16 clock ticks, that value appears on the output. But the value that you put in after this, that will also appear 16 clock ticks after that. So don't think of this as put in a value, tick the clock 16 times, read the output. Put in a second value, tick the clock 16 times, read the output. It's constantly keeping track of the last 16 inputs. Those are all stored in here. So if I input, a 0, 1, 0, 0, 1, 16 clock cycles later I'll see a 0, the next click I'll see a 1, and then a 0, and then a 0, and then a 1.
Would it be possible to make like an asynchronous shift register where we just take in a number, however many bits, and we want to shift all the bits at least that many times, right?
So asynchronous shift register would be interesting, because what would control the shifting then? So you could do something like, when this input is a 1, start shifting and everything starts moving down. And it would presumably move pretty quickly, but you could have some kind of delay in there. And then, when you bring the shift signal back down, it stops shifting and everything stays where it is. And that's a really different kind of circuit. And there's a whole discipline called asynchronous design that basically deals with that kind of approach to engineering. It's fabulously difficult to design and debug circuits when you don't have a clock like this. But the payoff is potentially huge. Potentially things work a lot faster and a lot lower power. But without the clocking to move everything, one step at a time, it's worlds harder to do. So this one is synchronous. So each time the clock ticks, there's a shift. There's another shift. There's another shift. And it looks a lot like Lab 6's delay circuit. It's a set of D flip-flops. Output of one feeds the input of the next. Clock them all together. The biggest challenge here is just getting the Verilog right. And that's partially trial and error, but there's also examples that are posted on Canvas that will help. And there's examples in the book. So there's a whole Verilog chapter in the textbook that you can refer to also. The most confusing experiment probably is experiment 4. So experiment 4 will use what you built in experiment 3. You want basically a circuit that detects if 5 of the last 16 inputs have been 1. So it looks almost identical to your shift register. It has an input, it has an output, it has a clock. But the output is basically telling you if in the last 16 clock ticks you saw exactly 5 logic 1 inputs. So there's a sample input output here. So here's our clock just ticking regularly, here's the input. So all through this period the inputs have all been 0. Okay, at this point it's seen a single 1. Okay, the output is still 0. At this point it's seen 2 1s, at this point it's seen 3 1s. And throughout this whole period, how many 1s has it seen? In the last 16 clock ticks, 3 of them. And then at this point it sees a 4th 1, and at this point it sees a 5th 1. So at this point right here, over the last 16 clock ticks, it's seen exactly 5 1s. That's where the output goes high. The next clock tick at this point, now over the last 16 clock ticks, it's seen 6 1s. Output goes low again. So this should always look back at your last 16 input events and see if exactly 5 of them were 1. And if it is, then and only then set the output to be 1. Now if this continues long enough, eventually the last 16 inputs will be these 3 ones and these 2 ones. This will have been 17 clock ticks ago, and at that point the output will go high again. And then on the next clock tick, the last 16 events would go back to this one. It would only have seen 4 ones, and so the output will go low again. And the trickiest part here is getting square in your mind what you want this circuit to do. And once you understand what the circuit should do, it's a pretty minor change to experiment 3. Because experiment 3, yeah, it's a shift register, but it's also remembering the last 16 inputs. And so all you need to do is add something to your circuit to say, hey, let's look at those last 16 inputs, see if exactly 5 of them were a 1. Does that make sense as far as the goal?
Yeah. Seems like remembering things is going to be interesting.
And it will remember them because you're going to have 16 D flip-flops. And, you know, your original input goes into the next flip-flop and the output goes into the next and so on. But in Verilog, we're not going to use the word D flip-flop. We're just going to have, you know, register A, register B, register C, register D. And we can do this thing we did on Tuesday where we said, you know, on the clock tick, copy C into D, copy B into C, copy A into B, copy A from the input. And these are the flip-flops, right? And this is having the effect of, you know, one flip-flop feeding another. But we're not describing the structure of our circuit, we're describing the behavior of our circuit. When the clock ticks, our input gets loaded into register A goes into B, and so on and so forth. But then at any point, we can look at these 1-bit registers, and we could see, you know, what their value is. So big hint here. Think about just adding up these 16 register values and see if that sum is meaningful somehow for experiment 4.
Can you do something like how you did on input and outputs in the lecture before, you go through like register, you know, test and then like bracket 0, bracket 1?
Yeah, so instead of doing A, B, C, D, you could, you know, have a register 15:0. And then you can do register bracket 0, register, you know, whatever you call this thing, data. You could do data bracket 0, data bracket 1, data bracket 2, and so on.
Cool.
There are for loops available in Verilog. My suggestion is stay away from them at this point. Right? If you try to do this, you might end up making 16 lines of Verilog. That's okay. Right? Do this in an editor that you're comfortable with. Lots of copy and paste, things like that. But for loops get really strange really quickly in Verilog, because there's for loops that would let you, you know, do some statement 16 times, and there's for loops that actually synthesize hardware. And if you get those confused, you create a whole new set of problems and challenges to deal with. Don't be afraid of writing Verilog code that looks like you're repeating yourself 16 times or 20 times or something. There's nothing wrong with long Verilog.
Is it just because for loops are just more complex? Is that why?
Because you have to be careful whether you're asking a for loop to replicate your Verilog code or to actually create hardware that performs a for loop. And if you try to synthesize hardware that's actually doing a for loop and a counter and a check and so on, you end up with a very different piece of hardware in the end.
Okay.
But, you know, definitely experiment. This is the only way to learn this stuff. And if you want to get better with Verilog, right, definitely go ahead and dig into that. All right, let's see. let's take a quick look at the homework. And the homework is almost, I think it's mostly easier than the lab.
Is it also just Verilog things?
So it's all just Verilog, yeah. And so here it notes, in addition to the code include design documentation. So don't just turn in a bunch of Verilog code. You got to explain what the code is doing and how it works. And you can do that by putting comments throughout the code, which I might recommend. Or you could, put a paragraph before or after the code saying what's going on. But your best approach is just put comments in the code itself. So write Verilog code to implement a function. So this is a pure combinational circuit. This is a bunch of assignment statements, or one assignment statement. Write Verilog code to implement a positive edge triggered D latch. Well, that's the solved problem. The unsolved is the T latch. So it's a clocked circuit. You're going to have an always block. And when the clock ticks, so always at positive edge clock, if the T input is 0, don't do anything. If the T input is 1, toggle your output. So as usual, the solved version will give you a lot of hints on doing the unsolved version. But if you take this and mimic it too closely and tweak it into the solution to the unsolved problem, you get the solution, but you don't get the learning, right? So you can expect, probably at least one Verilog question on the final. So you want to know how to write Verilog, and that comes from trying to do it, right? Write some code, throw it into the tool, simulate it, see if it works. If it doesn't, see what it is doing. Look at your code, try to figure out why it's doing that, and then try to figure out how to change it into something else, right? That's the back and forth trial and error learning process, which gets totally short-circuited if you look at the solved problem and try to change, from a D to a T, for example. So don't do yourself a disservice. All right, question 3, implement a positive edge triggered SR flip-flop. So you can go into the book and see what an SR flip-flop is supposed to do, because we haven't really dealt with those. Write a 4-bit binary down counter. Well, you're making an 8-bit up-down counter for lab, so if you can do that, just make it count down and make it only 4 bits. So 4U is a subset of one of your lab experiments. Write Verilog to implement a 3-bit to 8-line decoder. So 3 inputs, choose one of 8 lines. And so we did a 2-to-1 mux the other day. So same idea for here, same idea for this, 8-line to 3-line, or 8-line encoder. And then 7 is your traffic light, and I want to talk about that separately in a minute. 8 is an ALU, which adds, subtracts, and multiplies. So let's talk about that first. What is an ALU? So ALU is an arithmetic logic unit. It's a piece of a computer CPU. And a general block diagram would look like this. So we have an input A and an input B, and those are both 8 bits wide. And then we have some kind of function select. So we're supposed to design an ALU which can add, subtract, and multiply two 8-bit numbers. So maybe we'll have F0 and F1. And then here's an output. And so this might be our truth table. So maybe if I set my inputs for my function to be 0, 1, my output will be A plus B. If I set my function to 1, 0, my output will be A minus B. If I set it to 1, 1, my output will be A times B. And what should I do if there's 0, 0? I don't know. Maybe I'll just say I don't care what the output is. And so the idea is, here's one block of logic that I can feed two numbers into, and I can say, if I want to add these, I'll just put a 0, 1 here, and there's the sum. If I want to subtract, I'll put a 1, 0, there's the difference. If I want to multiply, I'll put a 1, 1, there's the product. And so this would sit inside a data path as part of a CPU, where there's other circuitry, multiplexers, for example, that choose different things to feed into A and B. Something that chooses what function we're trying to do. So if we've got a piece of C code which says, you know, x equals A times B, A would get sent here, B would get sent here. The compiler would generate binary instructions to say put a 1 here and a 1 here, which makes this thing a multiplier. And then the output would get sent through a demux into whatever X is, a register or a memory location. So all you're doing for 8 is the Verilog code for this block. And your output, probably 16 bits. Because if you multiply two 8-bit numbers, you might get 16 bits of output. If you add, you're going to get, 9 bits with a bunch of zeros to the left. And go ahead.
Types where it's like more than 8 inputs, right? Or more than 8-bit inputs, right?
What was the start of your question?
You can have an ALU with way more input bits, right? Okay.
Definitely. If you had a 64-bit CPU, you'd want a 64-bit ALU. But there's a really popular chip that's a 4-bit ALU. And a lot of these larger ones are built by just taking those 4-bit ones and putting them together. But in Verilog, right, we don't have to worry about that because we can, make these 8-bit registers. And how do we add them? We just set, assign out equals A plus B. Or out equals A times B to multiply, and so on and so forth. So the Verilog's a whole lot easier than what you might think. All right, let's tackle a traffic light. So our favorite three-way T intersection. Each side has red, yellow, and green. Car on the right has priority, 2 to 4 second transition. So this is lab 6, right? But implemented in Verilog. And as happens in this course, there's easier ways and more difficult ways to do this. So let me suggest what's probably an easier way. So you have 3 car sensors. Let me call it car west, car south, and car east. So those are the sensors. And we have 9 outputs. So we have red west, yellow west, green west, red east, yellow east, green east. I'll put in the south too. Red south, yellow south, green south. All right, so you've done this a bunch of times before, right? So how do we do this in Verilog? And I don't recommend trying to do what you did in Lab 6. In Lab 6, using the old green and the delayed old green was simpler than thinking of this as a general state machine. Okay, that was a trick that we used, which said if we just use a delay circuit, we can look at the old green and the delayed old green and figure out what color a light should be. But we can do something a lot easier if we're working directly in Verilog, which is to actually think of this as a state machine. But how do we describe the different states of this intersection? What do you think some of the things would be that we would use to describe or consider the state of our system? And this is always kind of like the big first question when you're designing a sequential circuit, for example, is what is the notion of state here? So any ideas what the different states might be for this?
Are they based off the inputs?
They're definitely going to be related to the inputs.
Say east goes, south goes, west goes.
Okay.
I feel
So
like that's
so the inputs are telling us where a car is. Looking at who goes tells us where we have a green light. And at most we have one green light at a time, right? We're not allowing two lanes to be green. So east could be green, south could be green, west could be green. Are there other states that are possible?
Based off the yellow lights, right?
You got yellow lights too. It's possible nobody has a green light. How many yellow lights could be on at once?
one.
Just one. Because you only turn yellow if you were green, and now you're losing permission. Since only one green can be on at a time, there's only going to be one yellow. So let's think about these following states. West green, south green, east green, west yellow, south yellow, east yellow. And if exactly one of these states is going to be active at any given time, assuming somebody always has a green light or a yellow light. In other words, you don't have a case where everybody's red. Then exactly one of these situations will describe the current state of the intersection. And if you know what the current state is, and you know where you have cars waiting, you can figure out what the new state should be. So for example, so east has highest priority. So suppose you're in east green, and there's a car to the east. You're just going to stay in this east green state, right? This light is green, there's a car sitting here, it's going to stay green. But if you're in east green, and there's no car to the east, but there's a car to the south, what should our new state be?
East yellow.
We should go to state east yellow. All right, if we're in state east yellow, and there's a car to the south, what should our next state be?
South green.
Yeah, you got it. If we're in east yellow and there's a car to the south, our new state should be south green. So there's two things here. The first is figuring out, based on your current state and these inputs, what should your next state be? And that's the part that you really need to design. And for each of these 6 states, it's a few, if statements if I write them like this. A few arrows from circle to circle if I write it like a state diagram. But work this out on paper in whatever language you like, as pseudocode or pictures or whatever works for you, to try to understand how the system moves from one state to another. If you're in east green, and there's no car to the east, and there's no car to the south, but there's a car to the west, then we're going to give that western car permission eventually, but first we're going to go to east yellow. And so in either of these cases, we're just going to say our new state is east yellow. But when we're in east yellow, if there's no car to the south, but there is a car to the west, then we're going to go to west green. So there's a 2-second clock available, and so we can use that to say, okay, when the clock ticks, let's figure out what our new state is. And so these conditions are evaluated every 2 seconds, so that, you know, if we had a green light and a car showed up to the south, well, our yellow light will come on. 2 seconds later, our logic will say, oh, we're in the yellow east state, and there's a car to the south, we'll go to the south green state. And that'll give you those nice controlled transitions. And then outside of all of that, once you understand how to move from state to state, then you need to actually set up these lights. But these lights you can set with a series of assignment statements. If I'm in the west green state, what does that mean? It means I want a green light here, red here, red here. So red west is a 0, yellow west is a 0, green west is run, red south is 1, yellow south and green south are 0, red east is 1, yellow east and green east are 0. This is a lot of writing and organizing on paper, and then, you know, 1 page of Verilog code. It's all about sort of figuring out what you want the system to do from the perspective of here's 6 states, how do we move from one to another? And then here's 9 lights, what should these lights be set to based on which state we're in? If you get this all the way down to where you've got Verilog code and it's written and you can put it into Aldec and you can simulate it and everything works great, that's fantastic, right? But if you don't get to that point, right, the whole grading for this question is based on how did you develop your solution. And I would much rather see, you know, a detailed development of your Verilog code, even if it doesn't work, right, than just see a timing diagram that works perfectly but no explanation of where it came from. Right? So spend some time on this problem figuring out how to re-envision your intersection in terms of states, and then try to put some code together for that. All right, and this is why I gave you an extra close to a week on the homework and lab. Plus, we started Verilog a little later. All right, questions on that? That's a lot of stuff, I know.
So that one is just going to be a lot of if statements.
It's mostly a lot of if statements. And we're going to take a 5-minute break, and then I want to show you how to do state machines in Aldec and look at the code it generates. And that can be useful to get some ideas on how to actually code something like this in Verilog. And you're allowed to use the state machine generator in Aldec, but you're going to want to write this Verilog code by hand. It's going to be easier than trying to lay this out as 6 states with a bunch of bubbles, because you have 3 inputs, right? Which means you would have 8 arrows coming from each circle. You're going to end up with 48 arrows and 6 circles, and that's going to be pretty messy. And if you work through it like this, it turns out to be a lot simpler. Because, for example, if there's a car to the east, we don't care about the other cars, right? If there's a car to the east, we want to respond to that. So, but we'll look at this in Aldec and get some ideas on how to code these things up with if statements or with case statements, which can save us some logic. All right. Let's do a 4-minute, 18-second break, and then we'll come back and play around with Aldec. That was a quick break, but better than nothing. All right, so let's talk about state machines in the Aldec software. And this is actually pretty fun, other than when it crashes. But you know, we use the Aldec tool. We can write Verilog files, so .v files, and we can simulate them and, you know, look at timing diagrams and so on and so forth. So there's also a capacity in here to create state machines directly. So let's build a simple state machine, and I'm thinking of just kind of doing a 2-bit counter. So we'll do something like this. And I'm going to, you know, state with an output value and a transition which I'm going to call go. And the idea is if my go input is a 1, I will move from one state to the next, and if my go input is a 0, I will pause my count. So I'll just kind of stay where I am. And I'll just set my output to be, you know, a 1 when I hit state 3. So, you know, this is an up counter that can be paused. So if go is equal to 1, I'll move from state to state. If go is equal to 0, I'll stay in whatever state I'm in. So we've done this, you know, in homeworks and such, and it's, you know, a bit of a pain to do, right? Big wide tables and flip-flops and K-maps. So if we tried to do this in Verilog directly, it's something like your traffic light experiment. So you would have something that tracks our current state, so a 2-bit register. And if our state is 0 and our go is equal to 1, then let's change our state to 1. If our state is 1 and go is 1, let's change our state to 2. And let's set our output to 1 if our state is 3, otherwise set our output to 0. So most of these tools, including Aldec, lets us do this using this state diagram instead of thinking about it in terms of Verilog. So I'm going to come here under File, and I'm going to say New. And I'm going to say New, well, I'll start with a new workspace. So let me call this go count. And we'll start with an empty design. We'll do Verilog. So all of this is the same as usual. But then instead of doing a new Verilog source, I'm going to say File New, and I'm going to say let's do a new state diagram. So this option down here. And we'll say next, and we'll do Verilog, and I'm going to call it go count. And now I'm going to set up inputs and outputs. Okay, so I know that I want a go input. I know that I want a z output, which is either a 0 or a 1. I'm also going to have a reset option, which will force me to go into state 0. And this is just this nod to the fact that the simulator will get confused if it doesn't know what the initial state is. It won't know what state to go into. If it doesn't know what state it's in, how does it know what the next state is? So I'm going to have a reset input, which will force us into a known condition. So this is like the reset on the counter. So let's have an input called reset. Let's have an input called go. Let's have an input, which will be our clock. And let's have an output called z. And I think that's all we need. Input go, reset clock, output z. Let's do next. Now it gives me a message saying you have not entered a clock port yet. Do you want port clock to be a clock? So I'm going to say yes. All right. So 3 inputs, 1 output. I'm going to leave everything else in its default state. And I'm just going to say finish. there we go. Okay, I was about to start getting worried. All right, so I'm gonna zoom in with my control scroll wheel, or maybe not. All right, so it's got my inputs, outputs up here. There's a clock, there's go, reset, Z is an output. And I'm going to start making my state diagram. So I'm going to go to FSM, that's short for finite state machine. I'm going to go to states and say state, and I'm going to drop a state right here, and one here, and one here, and one here. And then I'm going to hit escape. And so those are my 4 states, and I'm going to go to FSM, and I'm going to say, oh, actually I'm not. I'm just going to come over here, and I'm going to click inside, well, let's see. Alright, I'm going to try to find the tool I'm looking for. Okay, I'm going to go under Actions, and I'm going to say Transition. And I'm going to click inside here. Nope. Alright, hold on. We'll get there. How about Transitions, Transition? There we go. Okay, so I'm going to draw an arrow. Now if I just come over here, I'm just going to get an arrow. So I'm going to kind of come up a little and come down. And it'll turn it into a nice smooth arrow for me. And so I'm drawing a version of this picture, which now looks really strange. So these are going to be the transitions when my input is a 1. And so let me double click on this arrow, and I'll go to HDL, and there's a condition, and my condition is going to be go equals 1. And I'll double, yeah?
When you click on the arrow, it gives you the condition?
So I'm going to double click on the arrow.
Okay.
It's going to bring up this box. So it's telling me this is an arrow from state S2 to S3. I'm going to go to the box tab that says HDL.
Okay.
And there's a condition here, and I can specify a condition for this transition to fire. So there I'm going to type go double equal sign 1.
Okay.
And say OK, and then it will go ahead and add that to my drawing. So I'm going to do that on all 4 of my arrows. So if go is equal to 1, we've got these 4 transitions from one state to the next. And then we also had, you know, if the go input was equal to 0, we wanted to stay in our current state. So let me go ahead and add those transitions. So we'll do finite state machine, transitions, transition. Well, that was a weird looking arrow. And then I'll double click on these. Hit escape. Double click on these, go to HDL, and the conditions for these are go equals 0. Let me see if I can make this arrow look a little less interesting. No, I'm just going to leave it where it is. I could delete it and redraw it, but I'm not going to worry about it. Alright, so now I've got transitions for when go equals 1 and transitions for when go equals 0, which is just staying in the same state. So we're moving along here.
I think those were SEA handles that you could.
Yeah, and
use,
I've never quite gotten the hang of. And I was afraid that I would detach it.
Yeah, that looks detached.
There we go. That's
Yeah.
better. Cool. Thank you. All right. So there's our basic diagram. How are we doing on time here? We got time. All right. I'm going to double click out in the middle of empty space here and go to reset. No, I'm not going to worry about reset. So the only thing is I want to have a way to force it to go to state 1, S1, when I hit the reset line. If I double click inside one of these arrows, I bring up, you know, a property window, and I can see, for example, that the binary code for state S1 is 0, 0. The binary code for state S2 is 0, 1, and so on. And those are also displayed here. So I'm going to click in here, and let's see.
You're on state S1, 1, right?
I'm in state S1, which is coded as 0, 0. So you can change these labels also. Let me do that. Let me make it match my drawing. But this kind of reinforces the idea that these labels are pretty arbitrary. That's not 0, 2. That's 1, 0. They're just names. All right. So there's our 4 states. All right, let's go ahead and turn this into Verilog, and then we'll figure out how to simulate it. So there's my state diagram. I can just come down here under Design and say Compile All. And compiled, no errors, no warnings. So if I expand this box right here, I'll see a new file called gocount.v. So double click on that to open it up, and here's the Verilog code that was generated by the tool in response to my state diagram. So it created a module called gocount with inputs reset, go, and clock, and an output z. So it set these up to be inputs, set z as an output, set up wires for the inputs, and it changed z to be a register. Right? The reason z is a register is because, you know, when we are in a state, we're going to assign a value to z. It needs to remember that value. And this assignment's going to happen inside an always block. All right. So it's using some new constructs for us. So there's this define statement, which basically lets us create a symbol. So we're using the symbol S00 to stand for 2 single quote B00. So this is a Verilog way of describing a pattern of bits. So I can say I want 2 bits, so that's what the 2 and the quote and the B means, and then I can list what those 2 bit values are. So this is the binary number 00, this is the binary number 01. But throughout this code, instead of saying 2 quote B11, I can just say uppercase S11. It's a symbol. And that symbol is based on, you know, what I decided to call these states. If I called this state ha ha ha, and I recompile, and I look at my Verilog code, there's a symbol called ha ha ha, which is set to be, you know, the binary number 11. So this is just a convenience that's, you know, theoretically making the Verilog code a little easier to read. So let's compile all of that again. All right. It sets up a pair of registers. One is called current state, the other is next state. They're both 2 bits. Why are they 2 bits? Because we need 2 flip-flops to make a machine with 4 states. So it's calling these, you know, current state bracket 1, current state bracket 0. Oh, thank you. And then there's you know, some comments in here generated by the tool about what the transitions are going to be. So what's the actual Verilog do? So when we say go or the current state changes, we execute the following statements. And basically the action comes down here. It's a case statement. So look at the current state. If your current state is 0, 0 and go is 1, set your next state to 1. If your current state is 0 and go is 0, set your next state to 0. In other words, stay in the same state.
What are those baskets for?
So that's the way in Verilog that you say this is a symbol that was defined using this define statement. So if we didn't do that, we could say, you know, 2 single quote B 0 0. But this
Okay,
is
but it
this.
looks like it doesn't end after it. It looks like it goes into the if statement.
It's just it's just an oddity of Verilog syntax. It's a way to say this is a symbol.
Oh, okay.
So it's not actually like a quoted string.
That's it. Thank you.
Mm-hmm. So this is the guts of the state machine. If you're in this state and this is your input, then set your next state to this. If you're in this state and this is your input, set your next state to that. And these are all done with these non-blocking assignments, right? Remember, we want the less than followed by the equal sign when we do these assignments to registers. So that theoretically, you know, this would happen in parallel with other things. And then when the clock ticks, this always block will fire, which says on the positive edge of the clock, set the current state equal to whatever we set the next state to. So all of this is your combinational logic. This is that block that takes the outputs of the flip-flop, that's what your current state is, and the inputs to the system, that's what go is, and figures out what the next state should be. But we don't generate J and K inputs and T inputs and so on. We just say I want the next state to be 0, 1 or 1, 0 or 1, 1 and so on. And then this synthesizes a piece of circuitry so that when the clock ticks, if we want the current state to become 1, 1, it will set the inputs of the flip-flops appropriately to make that what the new output will be. So inside this is happening all of the controlling of flip-flop inputs that you did in your state machine synthesis homework. And we can tailor this machine, right? For example, right now it's set up for when the clock is rising. We could say let's make a machine for when the clock is falling, and if we compile that and we look at the Verilog, well, down here it's changed my always block to say on the negative edge of the clock. Let's go ahead and set the current state to whatever the next state should be. And so you have a lot of control over the machine through this tool. I'd like to get the reset figured out, and I did this last night.
This program is such a ginormous amount of options.
I know, and it's free, which is cool.
It must take so long to learn all the things. It's like that.
And most people don't learn all of it, right? So with all of these things, whether it's Eclipse or IntelliJ or, you know, the Aldec tool or MP Lab or, you know, lower level learning VI, learning swing, the trick is, you know, find a subset of things that lets you do what you want to do and get really good with those. And that's kind of a self-selecting set, because if you learn something that you don't end up using regularly, you'll forget it. And if there's something that you do over and over and over again, and you learn some new way to do that, you're going to remember it because you're going to be doing it a lot. And so kind of building up your toolkit is a big part of engineering and computer science. And getting some habits to let that toolkit kind of evolve over time as you grow and shift from one area to another, and so on and so forth. And that's part of the challenge of teaching, by the way, because I do this once a year, and then there's 51 weeks during which I don't touch it, and so I need to like relearn it. And apparently I learned how to reset the system last night, and I'm blanking on it now. But what's missing from this in order to be able to simulate is to create an action so that when the reset line goes high, we force ourselves into state 0. And
Could do Google.
Googling Aldec is a little tricky. So when I did this last night, I forgot to put a reset line in, and then it created a block for me down here, and I was able to add an action to that. But I tried to get fancy this time and put the reset when I created that top module. And I just don't think in the next 2 minutes I'm going to figure out how to make that happen. So we'll compile this up and simulate it on Tuesday next week. And we don't have time to do the simulation anyway. But the effect would be, right, we'd set up the clock to be just a running pulse train. We can set up the go signal to be random and have it periodically just change from one value to another. Drive the reset for a few clock ticks in the beginning, and then when you look at the waveform, you should see the system moving from one state to another whenever go is 1, and then just staying in its current state when go is equal to 0. Alright, what else can we do on here? We can change these codings. So if I wanted to do one hot coding, I could code this as a 0001. I could code this as a 0010. I could code this as a 0100, and I could code this as 1000. And if I compile that and look at the Verilog code, now my state is a 4-bit value. In other words, I'm using 4 flip-flops now. This is that one hot encoding where we only have a single flip-flop outputting a 1 at one time. And the 4 legal values are this. So you can see one flip-flop's 1, the others are 0. And based on the current state, well, this doesn't change at all. Right? This is exactly what we had before. Based on your current state and the input, change so that your next state is equal to, whatever our diagram said. And then when the clock ticks, it's still negative edge clock. Change the current state to be what we saved in the next state. So yeah, it's a really useful tool. If you're doing state machine design in industry, right, you really don't want to be making a state table by hand. It's error prone, it's time consuming, and it's really hard to modify. Right? If you finish your whole homework with 15 pages of state machine synthesis, and then someone says, oh yeah, I forgot, I want another state in there also that does this thing, right? You basically go back to the beginning and start over again. Well, here, I could just go ahead and I could say, let's add another state in here, and I could put some new transitions in, and I could figure out what code I wanted to have and just recompile, and you're good to go. And that's really the goal of all of these tools is rapid prototyping, rapid development. All right, keep going on the homework in the lab. I have office hours tomorrow. which will probably be fairly quiet because my other class's big assignment is due tomorrow morning before office. So if you got questions on lab and homework, you can probably catch me in office hours tomorrow. And then there's also hours Monday and Tuesday. So we'll play a little more with this on Tuesday, and then I want to take a look at something called Open Cores, which is an open source repository of Verilog code that you can use to build, new Verilog from old. So we'll take a look at that, and then we'll start wrapping up the course next week. 2 classes left, and then we're done. All right, have a good one. I will see you next
Verilog
time.
is on GitHub.
Say again?
I wonder how much Verilog is on GitHub.
Oh, there's a fair amount. Yeah, definitely.
Oh wow.
Yeah.
Lot.
All right, cool. Have a good one. I'll see you all next time.
Thank you.
Next time.
Weekend.
Thanks, you too.